Today, we will see the functions and the types of the MRI contrast agents. Tumor tissues have differing relaxation times than their corresponding normal tissues. The relaxation times of tumor tissues are, on average, slightly longer than those of normal tissues. As you see in this table, tumor tissue relaxation time is a little larger than normal tissue. In bone, also tumor tissues relaxation time is larger than that of normal tissues. Okay. In MR imaging, the tumor tissues may therefore be distinguished from the normal tissues. However, certain tumor tissues are physically comparable to their normal counterparts, and the relaxation time variation is minimal. In particular, the T2 relaxation times are often short, making it difficult to identify tumor tissues from normal tissues in an MR image due to the small difference in T2 relaxation times between tumor and normal tissues. To increase the contrast of the MR image and as a result, to identify the tumor tissue from the normal tissue in the MR image, contrast agents alter the relaxation times of the tumor or normal tissues. So if we use contrast agent, we can get more contrasted image. The rates of absorption of contrast agents in tumor and normal tissues differ. Due to the EPR, EPR means enhanced permeability and retention effect, the uptake of the contrast agent by the tumor tissue is typically greater than that by the normal tissue. Yet, microphases are present in organs like kidney and the liver to remove invading foreign materials. In those organs, there are no macrophages in cancer tissue, or their function is reduced. The Kupffer cell is a kind of liver macrophage. There are no Kupffer cells, or the function of the Kupffer cell is incomplete in liver cancer tissue. As a result, the contrast agents are observed by normal tissue but not by cancerous cells. As a result, the absorption rate of contrast agent in normal tissues is much higher than in malignant tissues. The visual contrast can be improved as a result of this. T1 and the T2 contrast agents are two types of contrast agents. The table summarizes the currently used clinical contrast agents. T1 contrast agents are those based on gadolinium or mangan, while Theta contrast agents are those based on iron oxide nanoparticles. High-density gadolinium or mangan-based agents, on the other hand, can be utilized as theta contrast agents. Low-density nanoparticle agents can also be utilized as T1 contrast agent in the same way. So in this table, you can see here gadolinium-based contrast agents and mangan-based contrast agents. Those are typically used for T1 contrast agents. On the other hand, these contrast agents are made of iron oxide nanoparticle. The size of nanoparticle is about less than 100 nanometer. And these contrast agents are used as T2 contrast agents. These are used as T1 contrast agents. The relaxation is enhanced by the use of a contrast agent, while a T1 contrast agent enhances T1 relaxation at the specific site. The MR signal intensity at that site increases, resulting in a bright image. As you can see in this figure, the recovering of longitudinal magnetization gives the T1 relaxation, and this curve represents the recovering of magnetization without contrast agent. If you use contrast agent, the relaxation become faster in this way. So we can see the faster recovery of normalization. Therefore, with T1 contrast agent, we have larger signal than those in the without contrast agents. So if the organs observe the contrast agent, T1 contrast agent, then the image at this site looks brighter than that without contrast agent. On the other hand, MR signal intensity decreases when the T2 relaxation is enhanced by the theta contrast agent, resulting in a darker image. In this figure, T2 relaxation curve is shown without contrast agent relaxation follows this curve. However, if you use theta contrast agent, then relaxation become faster. So decaying of transverse magnetization become faster. Okay, so we can see the signal will decrease in case without contrast agent. So both contrast agents, T1 and T2 contrast agents, enhance the radiation. And in T1 contrast agent, radiation, if the radiation enhances, then the signal will increase, and we can get the bright image at that site. On the other hand, if the T2 radiation enhances, then signal will decrease. So we can get the dark image at that site. The inner and the outer sphere processes both contribute to the relaxation of nuclear spins by paramagnetic contrast agents. The inner sphere process is caused by a chemical exchange interaction between the paramagnetic agent's bound water and the surrounding free water, which causes nuclear spins to relax faster, so has the effect on T1. In clinically used gadolinium-based contrast agents, gadolinium ions are formed as chelates. As a result, the chelates bound water can interact with surrounding free water continuously, increasing nuclear spin T1 relaxation. Because the inner sphere effect of most gadolinium chelate agents is greater than the outer sphere effect, which will be discussed later, they are employed as T1 contrast agents. On the other hand, the outer sphere process happens when paramagnetic agents diffuse across the free water. So nanoparticle, contrast agent, paramagnetic agents diffuse through the free water. Then relaxation of T2 relaxation will be enhanced. The random fluctuation of paramagnetic agents provide a local magnetic field inhomogeneity, which increases nuclear spin relaxation, has influence on T2. Because coated ferrite nanoparticle agents are completely encased by their coating material, the chemical exchange interaction inner sphere process does not occur, because ferrite nanoparticle is coated by compatible materials outside. So the inner sphere interaction between free water does not occur. Furthermore, ferrite nanoparticles have a far larger magnetic moment than gadolinium ions, resulting in higher magnetic field fluctuation and homogeneity. Magnetic nanoparticles are considered to be suitable T2 contrast agents because of this feature. Since 1980, the MRI has been utilized as a diagnostic tool. GDPA was the first contrast agent to be developed, and it has been in clinical uses since 1988. The paramagnetic gadolinium is used in this contrast agent to speed up the relaxation of protons modulation. Because gadolinium is poisonous, is generated with DTPA. The T1 relaxation is accelerated by the energy transfer between the gadolinium-bound water and the surrounding free water. We already discussed that previously. Gadolinium has been used in nervous system and whole body applications. One of the gadolinium-based agents, Evoester, is absorbed by the liver and removed from the body via kidney and gallbladder. As a result, this agent is utilized to diagnose liver and gallbladder disease. The macrophage's function is to get rid of foreign objects that have entered the body. There are no macrophages in cancer tissue, or their function is reduced. The Kupffer cell is a kind of liver macrophage. There are no Kupffer cells, or the function of Kupffer cell is incomplete in liver cancer tissue. As a result, the contrast agents are observed by normal tissue but not by cancerous cells. The normal tissue appears brighter in T1 weighted imaging than malignant tissue, allowing us to see the well contrast imaging due to the function of the contrast agents. The paramagnetic manganese can be used instead of gadolinium. Mangan DPOP and mangan EDTA-PP T1 contrast agents are mangan-based. Manganese is also poisonous, thus it must be chelated or incorporated into liposome. These contrast compounds are also used in the imaging of the liver. In 1990, iron oxide nanoparticle contrast agents were introduced. T2 contrast agents or nanoparticle agents are used to speed up T2 relaxation. Because of the faster T2 relaxation, when these agents are observed by normal tissues, the MR signals at normal tissue size are reduced relative to other tissues that do not observe the agents. As a result, the image contrast is improved. The iron oxide nanoparticles for contrast agents have diameters of around 5 to 10 nanometers, and the surface of the particles are coated with biocompatible compounds to reduce the iron oxide toxicity. The coating materials are dextran, PEG, and silica. As a result, the overall diameter of the contrast agent is a few tenths of nanometers. The liver, spleen, and lymph nodes, among other organs, are imaged using these nanoparticle T2 contrast agents. Castromark and autoscan T2 contrast agents, on the other hand, are utilized to image the digestive organs. The particle size of these contrast agents is relatively larger, around 300 nanometers in diameter, and they can be taken orally. CEST, chemical exchange saturation transfer contrast agents, are currently being researched. The materials that give the exchangeable protons are among these contrast agents. If the protons are exposed to the characteristic radio frequency pulse, the saturation modulation can be transferred to the surrounding protons, water. The proton's T2 relaxation process is accelerated as a result of this modulation transfer. Paramagnetic, lanthanide, and the CEST materials are chemically bonded in para-CEST contrast agents. The chemical shift is induced by the paramagnetic material while the exchangeable protons are provided by the cell material. The cell materials are made of sugar or amino acids. Because the protons are exchanged in response to an external RF field, this contrast agent has an on-off function. Another advantage is that frequency of the RF field can be adjusted by using different paramagnetic and cell materials. In this MRI image, you can see the brain image. In the brain, the blood-brain barrier prevents the contrast agents from reaching the tissues. However, tumors disrupt this barrier, allowing the agents to leak out of the blood capillaries into the tumor and beyond. The rate at which it does so helps to clarify and stage the tumor. So you can see here, this is tumor site, and the tumor site absorbs the contrast agents, but other tissues do not absorb the contrast agent due to the blood-brain barrier. But tumor tissue disrupt this barrier and absorb the contrast agent, and in the MRI image, this part looks brighter than other tissues. So effect of MRI contrast agent: T1 weighted images, left side image without, and right side image with a contrast medium, show defects of blood-brain barrier after stroke. So we can see the bright part, the tumor tissue site. When contrast agents are observed by normal tissues in liver, the T2 relaxation accelerates. The MR signal of normal tissues increases and appears brighter in the T1 weighted image as a result of the faster T1 relaxation. On the other hand, the brightness of tumor tissues does not change since the contrast agent is not taken up by the tumor tissues. Hence, compared to the normal tissues, the tumor tissues appear to be darker. You can see here. As a result, the contrast agent in the T1 weighted image can clearly identify substantially darker tumor tissues. When contrast agents are observed by normal tissues in liver, T2 relaxation accelerates. The MR signal of normal tissues decreases and they seem darker in the T2 weighted image as a result of the faster T2 relaxation. The contrast agent is not taken up by the tumor tissues, therefore the brightness of tumor tissues does not change. In comparison to the normal tissues, the tumor tissues just appear to be brighter. The contrast agent in the T2 weighted image can so clearly distinguish the bright tumor tissues. So if we use theater contrast agents, the normal site can absorb the contrast agent and looks brighter, and the tumor tissue cannot absorb the contrast agents. No, opposite side. Let me say again. Normal tissue can absorb the contrast agent, so T2 contrast agents. So the T2 relaxation process in the normal tissue enhances. So that means that we can have smaller signals from normal tissue. So if the normal tissue absorbs the contrast agents, the normal tissue will become darker. But the cancer tissue cannot absorb contrast agents. So the brightness of the cancer tissue does not change. So you can see here, tumor tissue, brightness of tumor tissue does not change with contrast agent, but the normal tissues, this size, normal tissue absorbs the contrast agents, and their T2 relaxation enhances, and it can have a low signal from the normal tissue. So normal tissue becomes darker. So we can clearly identify the tumor tissue. The magnetic materials can be divided into three groups based on how they react to an external field: paramagnetic, ferromagnetic, and diamagnetic. In the absence of an external field, ferromagnetic materials nevertheless exhibits magnetic behavior to the strong spin-spin interaction between magnetic dipoles. On the other hand, paramagnetic materials do not show magnetic behavior in the absence of magnetic field. Certain magnetic dipoles in paramagnetic materials align along the field when magnetic field is applied, but magnetic behavior vanishes when the field is withdrawn. The diamagnetic materials exhibit low magnetic behavior in opposite to the applied magnetic field. So you can see here, x-axis is the applied field intensity, and y-axis is magnetization. In paramagnetic materials, if we apply magnetic field, magnetic dipole line, and we have a non-zero magnetization. But if we shut off the magnetic field, outside magnetic field, then magnetization will become zero. The diamagnetic material, magnetization will be opposite to the field. And ferromagnetic material we can discuss in the next slide. Perimagnetic or ferromagnetic materials exhibit magnetic hysteresis. These materials have magnetic domains that range in size from 0.1 to a few millimeters when we examine inside of them. So if you look inside the ferromagnetic material, material can be divided into the domains, magnetic domains. Due to the strong interaction between magnetic dipoles, the magnetic moments of the atoms in the magnetic domain align to have non-zero magnetization in a specific direction. You can see here there are many magnetic domains. In each domain, magnetic dipoles are aligned due to the spin-spin interaction between dipoles. And I can see this magnetization in some direction, but the directions of magnetization are all different. Yet, because domains magnetization orientations are random, the material has no magnetization. So if we vector sum of this magnetization, then we can see it's zero magnetization. So no magnetic behavior can be seen. The area of domain along the field increases and the magnetization becomes non-zero when external magnetic field is applied to the ferromagnetic material. If we apply external magnetic field, then the area of the domain parallel to the field increases. Okay? So we can have a non-zero magnetization. With increasing field strength, the domain's area whose magnetization is along the field grows larger until only the domain along the field remains, a condition called as saturation. So we can have maximum magnetization because only the domain along the fields remains. In this situation, the material exhibits saturation magnetization, which is its maximum magnetization ms. So in this figure, still it's not saturated. If we use larger magnetic field, then it will be saturated. The magnetization also remains when the magnetic field is removed. This is known as remnant magnetization. If we remove the magnetic field at this position, so magnetic field is zero, right? But there is still some magnetization. So we call this as remnant magnetization. Applying the magnetic field that is opposed to the magnetization, so opposite direction, this direction, also known as coercive force, will remove this residual magnetization. So if we want to remove this random magnetization, we have to apply the field coercive force Hc. Then the magnetization will become zero. Okay. The saturation magnetization in opposite direction is obtained as the field of the opposing direction grows. So if we increase the magnetization opposite direction, then it will be saturated in this direction. So one cycle of hysteresis is finished if the field direction is switched once more while continuing to the preceding process. So we change the direction of the field and we follow the same steps as before, then we can have this kind of hysteresis behavior. Okay. In paramagnetic materials, there are no strong spin-spin interactions. Hence, there is no magnetic behavior. Because the interaction between dipoles is weaker than the thermal energy, the directions of magnetic dipoles in these materials are random. So, directions of magnetism of atoms are random. So, totally, we cannot see any magnetic behavior without field. Thus, only if an external field is applied can paramagnetic materials be magnetized. We apply the field, then some dipoles align to the field, so we can see the magnetic behavior. Some magnetic dipoles align the field and paramagnetic material in the field. However, unlike paramagnetic materials, the magnetization of paramagnetic materials is only observable when the field is applied. If we remove the field, then the directions of dipoles become random again, so no magnetic behavior. When the field is removed, the magnetization disappears. Okay. This data can show this behavior. If we use applied magnetic field, the material showed magnetic behavior, magnetization. But if we remove magnetic field, then magnetization will become zero. If the size of ferromagnetic nanoparticles is less than a certain value, usually less than 100 nanometer, the ferromagnetic nanoparticles only have one domain. So if we reduce the size of nanoparticles, then eventually we have just one domain, single domain. Okay. However, above a certain temperature, known as breaking temperature, the particles become paramagnetic because the interaction energy between particles is less than the thermal energy, and the magnetic moments of the particles become random. So this breaking temperature of nanoparticle, so usually the room temperature. The particles are called superparamagnetic because they become paramagnetic yet have a larger magnetic moment than typical paramagnetic particles. Superparamagnetic nanoparticles are utilized as MRI contrast agents. They have significant magnetic moment which causes hydrogen protons to relax more quickly, resulting in a more contrasted image. Now we'll show how we can make nanoparticle contrast agents. Superparamagnetic nanoparticle contrast agents. We first make nanoparticles and coating the particles. So synthesis of nanoparticles and coating is first process, and then we have to check the size of particles and shape of particles, and we have to check the coating status. And next, we have to check the crystalline structure using XRD, and we can also check the coating status using FTIR technique. Next, we have checked the supermagnetic properties using a vibrating sample magnetometer. And then we can make aqueous solutions of nanoparticles. So various concentration of nanoparticles in the aqueous solution. Using these samples, we can check the T1 and T2 relaxation times using MRI. And using this data, we can determine the reactivity. Reactivity we will discuss in the next slide, but this this value will tell us the control agents is applicable for the T1 or T2 control agents. And the final step, we will do the animal experiment using MRI. There are various ways of synthesis of nanoparticles. This slide shows several synthetic methods which was used in our laboratory. These are data for ketone coated nickel ferrite nanoparticles. The shape is rudder shape, and the length of the particle, average length of particle is about 16 nanometer, and the width of the rod, average width of rod is about 4 nanometer. So these are rod-shaped nanoparticle with width about 4 nanometer and length about 16 nanometers. And these are data for XRD, and this gives the correct ferrite structure. And this FTIR data shows that the coating material is firmly attached to the nanoparticle. This gives the magnetization data, and the magnetization is very large, 60 mU per gram, and this data also show the paramagnetic behavior of nanoparticles, and the magnetization is very large, so this is a super paramagnetic nanoparticles. This data is T1 and T2 relaxation. So from this data, we can determine the T1 and T2 relaxation times. And using data, we can plot T1 or T1 or T2 as function of concentration of another particle in the aqueous solution. So slope of this line gives T1 and T2 reactivity. And this image, MR image, shows this T1 weighted image and this T2 weighted images. This image clearly shows that the T1 and T2 contrast agents. This data is for the copper zinc ferrite particles. This particle is coated with silica. You can see here the particles are embedded inside the silica coating material, and the diameter of the size is around 100 nanometer. Okay. And this 10 image shows the cube-shaped nanoparticle, nickel mangan ferrite nanoparticles, and this nanoparticle show T1 and T2 contrast effects. The reactivity of contrast agents. The capacity to reduce reaction times is measured by reactivity of the T1 and T2 contrast agent. The reactivity of a contrast agent is defined as the rate of change in reaction time per unit mole, and represented as this equation. Here, tau I corresponds to reaction times with contrast agent, and tau IM corresponds to reaction time without contrast agent. And 1 and 2 represent T1 and T2. The reactivity and the concentration of the contrast agents in the contrast agent are represented by Ri and C respectively. The reactivity is measured in millimole -1 and the second -1. The contrast agent is designated as T1 or T2 depending on R1 to R2 ratio. Gadolinium or mangan-based contrast agents have a larger R1 over R2 ratio, so R1 is larger. R1 effect is larger than that of R2 effect, so indicating that they are T1 contrast agents. On the other hand, the iron oxide nanoparticle contrast agents have larger R2, making them T2 contrast agents. So, if we check R1 and R2, we can determine that their contrast agents can be used T1 or T2 contrast agents. Here are data for several contrast agents, and this one is data for GD-DTPA, the commercial contrast agent, and others are contrast agents which are made in our laboratory. So this gives the T1 reactivity, and this gives T2 reactivity, and GD-DTPA has a larger T1 reactivity. The slope of this curve gives T1 reactivity. So the slope of this T1 reactivity is larger than that of the T2 reactivity. for the GD-DTPA. So GD-DTPA is the T1 contrast agents. And the others are ferrite nanoparticle contrast agents. And for these ferrite nanoparticle contrast agents, T2 reactivity is much larger than T1 reactivity. So these nanoparticle contrast agents can be used as T2 contrast agents. Finally, I can show the MRI image for T1 or T2 contrast agents. These contrast agents are were made in our laboratory, and this contrast agent can both used as T1 or T2 contrast agents. This MRI image are T1 weighted images. The T1 weighted MR images of the rat before and after injection of nickel ferrite nanoparticle contrast agents are shown in the figure below. The T1 weighted MR images before and 5 minutes after the contrast agents injection are presented here. So the before injection of contrast agent and this 5 minutes after injection of contrast agents. The river is presented by the majority of the image. So this is a river of the red. When compared to the brightness of the image region marked with O, and this before the injection of the contrast agent, the brightness of the image region marked with O after injection of contrast agents increased by up to 25%. So the brightness after injection of contrast agents is 25% brighter than that without contrast agent. So the brightness of the liver with contrast agent is 25% larger than that the part without contrast agent. So this result shows that T1 effect of contrast agents represented here. So we can use this nickel ferrite nanoparticle contrast agents can be used as T1 contrast agents. This image shows the T2 weighted images. T2 weighted MR images of the rat before and after injection of the nickel ferrite nanoparticle, same nanoparticle contrast agents are shown in the figure below. T2 weighted MR images before, this is before, and 5 minutes after the contrast agent injection are shown here. When compared to the brightness of the image region marked O here, before the injection of the contrast agents, the brightness of the image region marked with O after injection of the contrast agent was reduced by up to 71%. So bright is after injection of control agents is reduced 71% reduced compared to that before the injection of the contrast agents. So this results show that these finite nanoparticles can also be used as theta contrast agent. As we already show in the previous slides, the T1 effect is 25%, right? But the T2 effect is 71%. So this nanoparticle contrast agent has a higher T2 effect than that of T1 effect. So this nanoparticle contrast agent is mainly used as a T2 contrast agent, but T1 effect is still there, so we can use this contrast agent as T1 contrast as well. These animal experiments results indicate that nickel ferrite nanoparticle contrast agent can be used both T1 and T2 contrast agents.